Hey everyone, welcome back. Today, we're going to pop the hood on a modern server and really look inside. We're talking about deconstructing the absolute core components of computing, from the physical silicon itself all the way up to the virtual layer that makes everything tick. Sound good? Okay, let's jump right in. At the heart of all this is one big central question. What's the real difference between the physical hardware, the stuff you can actually touch, and the virtual resources you're just clicking around and assigning in software? By the end of this, I promise you'll see exactly how they connect, and more importantly, why getting this right is a total game changer for performance. Okay, first things first, we have to start with the physical foundation. If you want to understand virtualization, you've got to get a handle on the hardware it's all built on. So let's start with the most basic connection point. So let's talk about a socket. What is it really? Well, it's pretty much exactly what it sounds like. It's the physical spot on the computer's motherboard, the main circuit board, where you plug in the brains of the whole operation, the CPU, or central processing unit. Yeah, the easiest way to think about it is just like a special kind of port, right? You've got USB ports for your mouse, HDMI for your monitor. Well, the motherboard has a CPU socket, and that's just for the processor. It's literally the physical gateway for all that incredible processing power. Now, here's something that's super important to get. A modern CPU isn't just one single thing. Nope, when you plug that one CPU into its socket, you're actually installing a bunch of little processing units inside it. We call those cores. So a single CPU might have 8 cores, like we see here, or 16, or even way more. You can really think of each core as its own independent little engine, just revving and ready to do some work. All right, so we've got our processors, and they've got their cores. But here's the thing. A processor is totally useless without data to chew on, and it gets that data from memory. And how it gets that data? Well, that is absolutely critical for speed. This brings us to a really important design decision in server architecture. So, back in the day, everything used what's called Uniform Memory Access, or UMA. The best way to picture this is like a small town with only one single lane road to the library. If everyone tries to go at once, you get a massive traffic jam. It's slow. The modern way is NUMA, or Non-Uniform Memory Access. Now this is much smarter. It's like giving each neighborhood its own local library branch with a super fast private highway to get there. It is way, way faster. So this really gets to the core idea of NUMA. Getting data from its own local memory, super fast, no problem. But what if it needs data that's attached to a different processor? Well, now it has to take a slower path to get to that remote memory. And that little grouping, a CPU and its own dedicated local memory, that's what we call a NUMA node. It's a fundamental building block. Okay, I think we've got a pretty solid grip on the physical hardware now. So let's switch gears. We're going to move up a layer and see how all this stuff gets translated into the world of virtualization. And this is where we finally meet the vCPU. So, a vCPU, or a virtual CPU, this is not something you can go buy at a store and hold in your hand. It's not physical. It's purely a software construct. Think of it as a virtual slice of the server's total processing power that you can hand out to a virtual machine or a VM. And if you remember one thing from this whole explainer, let it be this. A vCPU is not a physical core. I'll say it again, it is not physical core. It's an abstraction. It's just a promise, a representation of a certain amount of CPU horsepower that a VM is allowed to use. Everything else, that's handled by the system's manager, the hypervisor. And this is basically how it all works. It's a pretty simple process, really. Step 1, an admin says, okay, this new virtual machine gets, say, 4 vCPUs. Step 2, a special piece of software called a hypervisor jumps in. It acts like a traffic cop, and its job is to map the work from those vCPUs onto the actual physical cores. And step 3, the VM just goes about its business, using the power it was promised. It has no idea what's happening underneath. All right, so we've got sockets, we've got cores, we've got NUMA nodes, and now we've got vCPUs. This is the fun part. Let's put all these pieces together and see how they actually interact in a real-world server setup. So let's imagine a scenario. We've got a server, and this server's motherboard has 2 physical sockets, and into each one of those sockets, we're going to install a CPU that has 8 cores inside it. Pretty standard setup. So, quick math. How much raw physical power are we working with? Well, it's pretty simple. 2 sockets times 8 cores in each CPU, that gives us a grand total of 16 physical cores. That's our hardware budget. That's the total amount of power the hypervisor gets to play with. And because we have 2 sockets, each with its own CPU and its own local memory, guess what? This physical layout automatically creates two NUMA nodes. Now, a smart hypervisor knows this, and it's going to do its absolute best to keep a VM's vCPUs and its memory all bundled together inside a single node. Why? To make sure it always gets that super fast local memory access. Okay, so now we come to the big trade-off, the real balancing act. On one hand, you can under-provision. That means assigning fewer vCPUs than the 16 physical cores you actually have. The performance for each VM will be fantastic, but you might be wasting a lot of expensive hardware that's just sitting there doing nothing. On the other hand, you can over-provision. You could assign, say, 32 vCPUs. This is great for maximizing your hardware. You can cram more VMs on there, but there's a catch. Those 32 vCPUs now have to get in line and share the 16 physical cores, and that can really start to hurt performance. And really, that's the key takeaway here. The hypervisor software, it's incredibly smart. It does all these really clever tricks to schedule and manage the chaos when you over-provision, but it's not magic. At the end of the day, it's managing a limited, finite resource. And at a certain point, performance is gonna take a hit because you're just asking the hardware to do more than it can physically handle all at the same time. So this brings us right back to where we started. It's not really about just having 16 cores. The real question is, are you using them wisely? Are you letting expensive hardware sit idle, or are you pushing it so hard that your performance is tanking? Understanding all these layers, from the physical socket all the way up to the virtual vCPU, that is the secret to finding that perfect sweet spot, the perfect balance.